So hey everybody, today we are going to see unit 3, which is lists. So let's start. In the previous unit we have discussed arrays. Arrays are data structures of fixed size. Insertion and deletion involves reshuffling of array elements. Thus array manipulation is time consuming and inefficient. In this unit, we will see abstract data type lists, array implementation of lists, and linked list implementation, doubly and circular linked lists, and their applications. In linked list, items can be added or removed easily to the end or beginning or even in the middle. Objectives. After going through this unit, you will be able to define and declare lists, understand the terminology of singly linked lists, understand the terminology of doubly linked lists, understand the terminology of circularly linked lists, and use the most uh, appropriate list structure in real life situations. Now comes abstract data type list. Abstract data type ADT is a useful tool for specifying the logical properties of data type. An ADT is a collection of values and a set of operations on those values. Mathematically speaking, a type is a set and elements of set are values of that type. ADT list. A list of elements of type T is a finite sequence of elements of type T together with the operations of create, update, delete, testing for empty, testing for full, finding the size, traversing the elements. In defining abstract data type, we are not concerned with space or time efficiency as well as about implementation details. The elements of a list may be integers, characters, real numbers, and combination of multiple data types. Consider a real world problem where we have a company and we want to store the details of employees. To store this, we need a data type which can store the type details containing names of employee, date of joining, etc. The list of employees may increase depending on the recruitment and may decrease on retirements or termination of employees. To make it very simple and for understanding purposes, we are taking the name of employee field and ignoring the date of joining, etc. The operations we have to perform on this list of employees are creation, insertion, deletion, visiting, etc. We define employee underscore list as type def struct curly braces open char name 20, and under that we will be code and will be closed by curly braces employee underscore list semicolon. Operations on emp underscore list can be defined as create underscore employee emp underscore list into emp underscore list. Here we will be writing create function by taking help of C programming language. So the list has been created and name is a valid entry in empty list and emp list, and position p specifies the position in the list where name has to insert it. Insert underscore emp underscore list into emp underscore list char into name int position curly braces open. Here we will be writing insert function by taking help of C programming language. Delete underscore emp underscore list into emp underscore list char into name. Here we will be writing delete function by taking help of C programming language. Curly braces closed. Visit underscore emp list. Emp underscore list into emp underscore list. Here we will be writing visit function by taking help of C programming language. The list can be implemented in two ways: the contiguous array implementation and the linked pointer implementation. In contiguous implementation, the entries in the list are stored next to each other within an array. The linked list implementation uses pointers and dynamic memory allocation. We will be discussing array and linked list implementation in our next section. Array implementation of lists. In the array implementation of lists, we will use array to hold the entries and a separate counter to keep track of the number of positions are occupied. A structure will be declared which consists of array and counter. Type def struct curly brace open int count int entry 100 list semicolon. Mm, For simplicity, we have taken list entry as integer. Of course, we can also take list entry as structure of employee record or student record, etc. Count. So here you can see. Now comes insertion. In the array implementation of lists, elements are stored in continuous locations. To add an element to the list at the end, we can add it without any problem. But suppose if we want to insert the element at the beginning or middle of the list, then we have to rewrite all the elements after the position where the element has to be inserted. We have to shift nth element to n plus 1th position, where n is number of elements in the list, the n minus 1th element to nth position, and this will continue until the rth element to r plus 1th position, where r is the position of insertion. For doing this, the count will be incremented. From the above example, if we want to add element 35 after element 33, we have to shift 77 to 8th position, 66 to 7th position, and so on, 44 to 5th position before insertion. So here you can see step count, step 1, step 2, step 3, step 4. You can pause and see the table. Okay. So figure program 3.1 will demonstrate the insertion of an element at desired position. This is one of the important topics. Inserting an element into contiguous list linear array at specified position. Contiguous underscore list point C hash include stdio.h. Definition of linear list type def struct curly braces open int data 10 int count list. Prototypes of functions: void insert list into int void create list in asterisk, void traverse list into list. Okay. Definition of the insert function: void insert list asterisk star into position into element. Int temp is equal to start minus greater than count, while temp is greater than equal to position. Curly braces open start minus greater than data temp plus 1 start minus greater than data temp minus minus semicolon. Curly braces close start minus greater than data position is equal to element start minus greater than count plus plus semicolon. Curly braces close. Definition of create function: to read data values into the list. Void create list asterisk star int curly braces open int I is equal to 0 test is equal to 1. So you can see the program. We will just go fast. Okay, so here we were int I is equal to 0, test will be 1, while test f slash um, std in printf input value for percentage d 0 to come out I scanf d and star minus greater than data I if star is minus greater than data is equal to 0, test equal to 0, else I plus plus start minus greater than count is equal to 1 equal to I output function to print on the console. So void travis list strict start in type for I is equal to 0, I is less than start minus greater than count I plus plus printf value at the position percent d I start minus greater than data I main function void main in position element list I create and L is it L or 1 list 1 create. Okay, if it please comment in the comment section, is it I or L or 1. Print f enter list as follows. Now we are taking it as 1. Okay, f flash std in travis and 1. So fl is std in printf input the position where you want to add a new data item. Scanf and position f flash std in printf input the value for the position scanf and element insert and one position element traverse insertion of an element into a linear array. Deletion to delete an element in the list at the end we can delete it without any problem, but suppose if we want to delete the element at the beginning or middle of the list, then we have to rewrite all the elements of the position or the element that has to be deleted exists. We have to shift r plus 1th element to r position where r is position of deleted element in the list, the r plus 2th element to r plus 1th position, and this will continue until the nth element to n plus 1th position, where n is the number of elements in the list and then the count is decremented. From the above example, if we want to delete an element 44 from list, we have to shift 55 to 4th position, 66 to 5th position, 77 to 6th position. So before deletion, you can see the table here. Okay, and here you can read the program also. Okay, here you can read the program. Okay, how much is left? So much is there, yes, much is there. Okay, so there is only one check your progress, so it can be a little long video. So let's see, where were we? We were here before deletion. Declaration of delete list function. Void delete underscore list is list star int. Definition of delete underscore list function. The position of the element is given by the user and the element is deleted from the list. Void delete underscore list star start int position, int temp is equal to position, printf backslash n information which we have to delete, percentage d 1 minus greater than data position, while temp is less than equal to start minus greater than count minus 1. Start minus greater than data temp is equal to start minus greater than data temp plus 1. Temp plus start minus greater than count is equal to start minus greater than count minus 1. Main function void main. Print f backslash and input the position of element you want to delete. Scanf percentage d and position f flush std in. Delete underscore list and 1 position traverse and 1. So let's start with linked list implementation. The linked list is a chain of structures in which each structure consists of data as well as pointer, which stores the address link of the next logical structure in the list. A linked list is a data structure used to maintain a dynamic series of data. Think of a linked list as a line of bogies of train where each bogie is connected on to the next bogie. If you know where the first bogie is, you can follow its link to the next one. By following links, you can find any bogie of the train. When you get to a bogie that isn't holding linked onto another bogie, you know you are at the end. Linked lists work in the same way, except programmers usually refer to nodes instead of bogies. A single node is defined in the same way as any other user defined type or object, except that it also contains a pointer to a variable of the same type as itself. We will be seeing how the linked list is sorted in the memory of the computer. In the following figure 3.1, we can see that start is a pointer which is pointing to the node which contains data as Madan, and the node Madan is pointing to the node Mohan, and the last node Babu is not pointing to any node. 1000, 1050, 1200 are memory addresses. So here you can see a singly linked list. Consider the following definition. Type def struct note int data struct note into next list. Once you have a definition for a list node, you can create a list simply by declaring a pointer to the first element called the head. A pointer is generally used instead of a regular variable. List can be defined as list into head. It is as simple as that. You now have a linked list data structure. It isn't altogether useful at the moment. You can see if the list is empty. We will be seeing how to declare and define list using pointers in the following program 3.3. Hash include stdio.h type def struct note int data struct note point uh, star next list int main list star head is equal to null. Initialize list head to null. If head is equal to null, printf the list is empty \n. So creation of a linked list. In the next example program 3.4, we shall look to the process of addition of new nodes to the list with the function create underscore list. Hash include stdio.h hash include stdlib.h define null 0 struct linked underscore list int data struct linked underscore list star next type def struct linked underscore list void main list star head void create list star int count list star void traverse list star head is equal to list star malloc size of list create head printf backslash and traversing the list. Traverse head printf number of elements in the list. Percentage d count head. Void create list uh, star start. Printf input the element 1111 for coming out of the loop. Scanf percentage d and start minus greater than data. If start is minus greater than data equal to minus 1111, start is minus greater than next is equal to null. Else start is minus greater than next is equal to list. Star malloc size of list create star minus greater than next. Void traverse list star start. If start is minus greater than next not equal to null. Printf percentage d minus minus greater than start minus greater than data traverse start minus greater than next. Int count list star start. If start is minus greater than next is equal to null, return 0, else return 1 plus count start minus greater than next. Program 3.4 Insertion of elements into a linked list. Algorithm insertion of element into a linked list. Step 1 begin. Step 2 if the list is empty or a new element comes before the start head element, then insert the new element as start element. Step 3 else if the new element comes after the last element, then insert the new element as the end element. Step 4 else insert the new element in the list by using the find in function. Find function returns the address of the found element to the insert underscore list function. Step 5 end. Figure 3.2 depicts the scenario of a linked list of two elements and a new element which has to be inserted between them. Figure 3.3 depicts the scenario of a linked list after insertion of a new element into the linked list of figure 3.2. Before insertion, F is so here you can see the diagram before insertion and then okay, you can see the after insertion. Program 3.5 depicts the code for the insertion of an element into a linked list by searching for the position of insertion with the help of find function. Insert function. Prototypes of insert and find functions. List star insert underscore list list star list star find list star int. Definition of insert function. List star insert underscore list list star start list star n star f int key element. Print f enter value of new element. Scanf percentage d and element. Print f enter value of key element. Scanf percentage d and key. If start is minus greater than data equal key, n is equal to list star malloc size of list. N minus greater than data equal to element. N minus greater than next is equal to start. Start is equal to n. else f is equal to find start key. If f is equal to null, print f key is not found. Else n is equal to list star malloc size of list n minus greater than data equal to element n minus greater than next is equal to f minus greater than next. F minus greater than next is equal to n. Return start. Definition of find function. List star find int key. If start is minus greater than next minus greater than data is equal to key, return start. If start is minus greater than next is equal to null, return null. Else find start minus greater than next key. Void main list star head void create list star int count list star void traverse list star head is equal to list star malloc size of list create head printf traversing the created list traverse head printf number of elements in the list percentage d count head is equal to insert underscore list head printf traversing the list after insert \n traverse head. So program 3.5 insertion of an element to a linked list as a specific position. You can see the algorithm deletion of an element from the linked list. Step 1 begin. Step 2 if the list is empty then element cannot be deleted. Step 3 else if element to be deleted is first node then make the start head to point to the second element. Step 4 else delete the element from the list by calling find function and returning the found address of the element. Step 5 end. Figure 3.4 depicts the process of deletion of an element from a linked list. After deletion, you can see here deletion of an element from the linked list. Dotted line depicts the link prior to deletion. Program 3.6 depicts the deletion of an element from the linked list. It includes a function which specifically searches for the element to be deleted. Delete list function. Prototype of delete underscore function. List star delete underscore list star find list star int. Definition of delete underscore list star delete underscore list star start int key list star f star temp printf. Enter the value of element to be deleted. Scanner percentage d and key. If star minus greater than data equal to key temp is equal to start minus greater than next. Free start is equal to temp else f is equal to find start key. If f is equal to null printf key not found else temp is equal to f minus greater than next minus greater than next. Free f minus greater than next f minus greater than next is equal to temp. Return start void main list star head void create list star head void create list star int count list star void traverse list star head is equal to list star malloc size of list create head. Printf traversing the created list traverse head. Printf number of elements in the list percentage d count head is equal to insert head Printf traversing the list after insert. Traverse head is equal to delete underscore list head. Printf traversing the list after delete underscore list. Traverse head doubly linked list. So here we can see doubly linked list implementation. In a singly linked list, each element contains a pointer to the next element. We have seen this before. In single linked list, traversing is possible only in one direction. Sometimes we have to traverse the list in both directions to improve performance of algorithms. To enable this, we require links in both the directions. That is, the element should have pointers to the right element as well as to its left element. This type of list is called doubly linked list. So you can see the diagram. A doubly linked list is defined as a collection of elements, each element consisting of three fields: pointer to left element, data field, and pointer to right element. Left link of the leftmost element is set to null, which means that there is no left element to that, and right link of the rightmost element is set to null, which means that there is no right element to that. Algorithm creation. Step 1, begin. Step 2, define a structure element with fields, data, left pointer, right pointer. Step 3, declare a pointer by name head and by using malloc memory allocation function. Allocate space for one element and store the address in head pointer. Head is equal to element star malloc size of element. Step 4, read the value for head minus greater than data. Head minus greater than left is equal to null. Head minus greater than right is equal to element star malloc size of element. Step 5, repeat step 3 to create required number of elements. Program 3.7 depicts the creation of a doubly linked list. Creation of a doubly linked list. dblink.c hash include stdio.h hash include malloc.c struct dl underscore list int data struct dl underscore list star right struct dl underscore list star left type dev struct dl underscore list dlist void dl underscore create dlist star void traverse dlist star. Function creates a simple doubly linked list. Void dl underscore create dlist star start. Printf input the values of the element -1 1 1 1 to come out. Scanf percentage %d and start minus greater than data. If start minus greater than data is not equal to -1 1 1 1, start minus greater than right is equal to dlist star malloc size of dlist start minus greater than right minus greater than left is equal to start minus greater than right minus greater than right is equal to null. dl underscore create start minus greater than right, else start minus greater than right is equal to null. Display the list void traverse the list star start. Printf traversing the list using right pointer / and do. Printf %d is equal to start minus greater than data. Start is equal to start minus greater than right, while start minus greater than right show value of last start only one time. Printf traversing the list using left pointer / n. Start is equal to start minus greater than left. Do. Printf %d is equal to start minus greater than data. Start is equal to start minus greater than left, while start minus greater than right. Void main. D list star head. Head is equal to D list star malloc size of D list. Head minus greater than left is equal to null. Head minus greater than right is equal to null dl underscore create head. Print f created doubly linked list is as follows. Traverse head. So output input the values of the element -1 1 1 1 to come out 1. Input the element of -1 1 1 to come out 2. Input the values of the element -1 1 1 1 to come out 3. Input the values of the element -1 1 1 to come out -1 1 1 1. Created doubly linked list is as follows. Traversing the list using right pointer 1 2 3. Traversing the list using left pointer 3 2 1. Circularly linked list implementation. A linked list in which the last element points to the first element is called circular linked list. The chains do not indicate first or last element. Last element does not contain the null pointer. The external pointer provides a reference to starting element. The possible operations on a circular linked list are insertion, deletion, and traversing. Figure 3.6 depicts a circular linked list. Head list you can see here. Program 3.8 depicts the creation of a circular linked list. Hash include stdio.h, hash include stdlib.h. Struct linked underscore list, int data struct linked underscore list. Star next. Type def struct linked underscore list, clist clist star head star s void main void create underscore clist star int count clist star void traverse clist star head is equal to clist star malloc size of clist s is equal to head create underscore clist head. Print f traversing the created clist and the starting addresses %u traverse head. Printf number of elements in the clist %d count head. Void create underscore clist star start. Printf input the element -1 1 1 1 for coming out of the loop. Scanf %d and star minus greater than data. If start minus greater than data is equal to -1 1 1 1, start minus greater than next is equal to s. Else start minus greater than next is equal to clist star malloc size of clist create underscore clist start minus greater than next. Void traverse clist star start. If start minus greater than next is not equal to s, print f data is %d underscore t next element address is %u \n start minus greater than data start minus greater than next traverse start minus greater than next. If start minus greater than next is equal to s, printf data is %d \t next element address is %u \n start minus greater than data start minus greater than next. Int count clist start. If start is minus greater than next is equal to s, return 0, else return 1 plus count start minus greater than next. Creation of a circular linked list algorithm. Insertion of an element into a circular linked list. Step 1 begin. Step 2 if the list is empty or new element comes before the start. head element, then insert the new element as start element. Step 3. Else if the new element comes after the last element, then insert the new element at the end element and adjust the pointer of last element to the start element. Step 4. Else insert the new element in the list by using the find function. Find function returns the address of the found element to the insert underscore list function. Step 5. End. If new item is to be inserted after an existing element, then call the find function recursively to trace the key element. The new element is inserted before the key element by using above algorithm. Figure 3.7 depicts the circular linked list with a new element that is to be inserted. Figure 3.8 depicts a circular linked list with the new element inserted between first and second nodes. Figure 3.7. So here you can see, okay, here the figure is not clearly visible. Okay, so figure 3.8, you can see a circular linked list after insertion of the new element between first and second nodes. Dotted lines depict the links prior to insertion. Now comes program 3.9 depicts the code for insertion of a node into a circular linked list. Hash include stdio.h, hash include stdlib.h. Define null is 0, struct link underscore list in data struct link underscore list, and star next type def struct link underscore list c list, star head star as prototype of find and insert function c list star find c list star int c list star insert underscore c list star definition of insert underscore c list function, and c list star insert underscore c list star c list, star nl n1 int key x printf enter value of new element, scanf percentage d and x printf enter value of key element, scanf percentage d and key if start minus greater than data is equal to key, n is equal to c list star malloc size of c list, n minus greater than data is equal to x, n minus greater than next is equal to start is equal to n, else n1 is equal to find start key. If n1 is equal to null, printf key is not found, else n is equal to c list star malloc size of c list, n minus greater than data is equal to x, n minus greater than next is equal to n1 minus greater than next, n1 minus greater than next is equal to n. Return start. Definition of find function: clist star find clist star start int key if start minus greater than next minus greater than data is equal to key, return start if start minus greater than next minus greater than next is equal to null, return null, else find start minus greater than next key, void main void create underscore clist star int count clist star void traverse clist star head is equal to clist star malloc size of clist, s is equal to head create underscore clist head, printf traversing the created clist and the starting address is percentage %u traverse head, printf number of elements in the clist percentage d count head is equal to insert underscore clist head, printf traversing the clist after insert underscore clist and starting address is percentage %u comma head. Traverse head void create underscore c list star start print f input the element -1111 for coming out of the loop scanf percentage d and star minus greater than data if start minus greater than data is equal to -1111 start minus greater than next is equal to s else start minus greater than next is equal to c list star malloc size of c list create underscore c list start minus greater than next void traverse c list star start if start minus greater than next is not equal to s printf data is percentage d next element address is percentage u backslash n start minus greater than data start minus greater than next traverse start minus greater than next if start minus greater than next is equal to s printf data is percentage d backslash t next element address is percentage u backslash n start minus greater than data start minus greater than next int count clist star start if start minus greater than next is equal to s return 0 else return 1 plus count start minus greater than next insertion of a node into a circular linked list figure 3.9 depicts a circular linked list from which an element was deleted algorithm deletion of an element from a circular linked list step 1 begins step 2 if the list is empty then element cannot be deleted step 3 else if element to be deleted is first node then make the start head to point to the second element step 4 else delete the element from the list by calling find function and returning the found address of the element step 5 end so here we can see okay figure 3.9 is circular linked list from which an element was deleted dotted line shows the link that existed prior to deletion program 3.10 depicts the code for the deletion of an element from the circular linked list hash include stdio.h hash include stdlib.h define null 0 struct linked underscore list int data struct linked underscore list star next type def struct linked underscore list c list star head star is prototype of find and delete underscore function c list star delete underscore c list star find c list star int definition of delete underscore c list star delete underscore c list stars start int key c list star f star temp print f enter the value of element to be deleted scanf percentage d and key if start minus greater than data is equal to key temp is equal to start minus greater than next free start is equal to temp else f is equal to find start key if f is equal to null print f key not found else temp is equal to f minus greater than next free f minus greater than next is equal to temp return star definition of find function c list star find c list star start int key if start minus greater than data is equal to key return start if start minus greater than next is equal to null return null else find start minus greater than next key void main void create c list int count c list void traverse c list head is equal to c list malloc size of c list s is equal to head create c list head print f traversing the created c list and the starting address is percentage u head traverse head printf number of elements in the c list percentage d count head is equal to delete underscore c list head. Print f traversing the c list after delete underscore c list, and the starting address is percentage u underscore n head traverse head void creates underscore c list. C list star start printf input the element -1111 for coming out of the loop. Scanf percentage d and start minus greater than data if start minus greater than data is equal to -1111. Start minus greater than next is equal to s. Else start minus greater than next is equal to c list star malloc size of c list. Create c list start minus greater than next void traverse c list star start if start minus greater than next is not equal to s. Now printf data is percentage d, next element address is percentage u, start minus greater than data start minus greater than next traverse start minus greater than next if start minus greater than next is equal to s. Printf data is percentage d, next element address is percentage u, start minus greater than data start minus greater than next. Int count c list start if start minus greater than next is equal to s, return 0, else return 1 plus count start minus greater than next. Deletion of an element from the circular linked list. Applications. Lists are used to maintain polynomials in the memory. For example, we have a function fx is equal to 7x to the power 5 plus 9x to the power 4 is equal to 6x to the power 3 plus x square. Figure 3.10 depicts the representation of a polynomial using a singly linked list 1000, 1050, 1200, 1300 memory addresses. So here we can see the presentation of a polynomial using a singly linked list. Okay, now polynomial contains two components, coefficient and an exponent, and x is a formal parameter. The polynomial is a sum of terms each of which consists of coefficient and an exponent. In computer, we implement the polynomial as list of structures consisting of coefficients and exponents. Program 3.11 accepts a polynomial as input. It uses linked list to represent the polynomial. It also prints the input polynomial along with the number of nodes in it. Presentation of polynomial using linked list. Hash include stdio.h, hash include malloc.h struct link, char sign int coef, int export struct link star next, type def struct link poly, void insertion poly star void create poly create underscore poly star void display poly star function create a polynomial list void create underscore poly star start char ch static int I print f input choice and for break ch is equal to get char or and open if char is not equal to n. Print f input the sign percentage d I plus 1. Scanf percentage c and start minus greater than sign. Print f. Input the coefficient value percentage di plus 1. Scanf percentage d and start is minus greater than so coef coef and print f. Input the exponent value percentage di plus 1. Scanf percentage d star start minus greater than expo f flush stdini plus plus start minus greater than next is equal to poly star malloc size of poly create underscore poly start minus greater than next else start minus greater than next is equal to null. Display the polynomial void display poly star start if start is less than is minus greater than next is not equal to null. Print f percentage c start minus greater than sign. Print f percentage d start minus greater than coef. Print f x percentage d start minus greater than expo display start minus greater than next. Counting the number of nodes and int count poly count underscore poly star start and if start minus greater than next is equal to null return 0 else return 1 plus count underscore poly star minus greater than next. Function main void main poly star head is equal to poly star malloc size of poly create underscore poly head print f total nodes is equal to percentage d count underscore poly head display head. So here we come to the end and here it is check your progress. Let's see the summary. The advantage of lists over arrays is flexibility. Overflow is not a problem until the computer memory is exhausted. When the individual records are quite large, it may be difficult to determine the amount of contiguous storage that might be needed for the required arrays. With dynamic allocation, there is no need to attempt to allocate in advance. Changes in list insertion and deletion can be made in the middle of the list more quickly than in the contiguous lists. The drawback of lists is that the links themselves take space, which is in addition to the space that may be needed for data. One more drawback of lists is that they are not suited for random access. With lists, we need to traverse a long path to reach a desired node. So here we come to the end and till then keep exploring.